Welcome back to another Problem Corner solution. This is done in conjunction with the International Group for Mathematical Creativity and Giftedness. They are also known as IGMCG, and their website is igmcg.org. You should check them out. They are a very interesting group that focuses on creativity within mathematics and the education of that. They have their upcoming 14th conference this year in Karlstad, Sweden, and it's in June. You might want to attend it if you happen to be in Europe. That might be great, or even if you're not in Europe, maybe try to head over there and see what it's all about. But first, go down and peruse their website and see what they do. You might want to get involved and become a member of their group. This newsletter is done by Editor-in-Chief Scott Chamberlain out of the University of Wyoming and Associate Editor Chris Weiss out of Ohio University. So this is the March 2025 newsletter number 24. Problem Corner Solution, and this time we have gone with a recent problem from the AMC 12 and AMC 10. It was problem 17 for the 12 and problem 23 for the 10A in 2024. AMC is the American Mathematics Competition. It's held annually in the United States. There are 2 tests. International students are welcome to take the test. It is made by the Math Association of America. That's a lot to say. Let's get to the problem. Integers a, b, and c satisfy ab plus c equals 100, bc plus a is 87, ca plus b is 60. What is ab plus bc plus ca? So I think of this problem as kind of like the analogy that I gave in my write-up on the newsletter is that it's a little bit like one of those 3D puzzles with like little levers on it where you try to disentangle 2 objects or something like that. Metaphorically speaking, it's a little bit like that. You're going to move these things around in the equations, and if you play with it long enough, you should be able to figure it out. So I'm going to go through this the way that I solved it recently before I did this video, and I'm going to take false paths because why? We don't know when we start a problem exactly what we should be doing, and that's, you just try things and you see what happens and you explore and see where the weaknesses in the problem lie. So for instance, when you see this expression, my first thought is, hey, if I add this, this, and this, the 3 equations together, I might be able to create what I want right here. So I'm going to write AB plus C is 100, BC plus A is 87, and CA plus B is 60. Obviously 147 and 100 is 247, and so you have 247 is equal to what we want, AB plus BC plus CA plus an additional term of A plus B plus C. Didn't have enough space there to fit it in. So this is what we're looking for ultimately, but we're left with this other term. What might we do with that? So from there, it was kind of a thought of, where else have I seen this? Where I have 3 things. I mean, it's half the surface area of a parallelepiped, otherwise known as a box. And when you think about y, the dimensions, length, width, height, you have the base, if you draw it right, you have a base here of AB, so the area is the product AB, and there'll be 1 on the base and 1 on the top face, and you're going to get 2 of those for all 3 sides, or all 6 sides. There's a duplicate one, right? So this is half of the total surface area of a box with dimensions A, B, and C. Could we use that? Don't know. Where else have we seen it? It's part of Vieta's formulas for cubic polynomials. If you had, for example, ax squared plus, or ax cubed plus bx squared plus cx plus d equals 0, the letter c over a, that ratio of those coefficients is the sum of the pairwise products of the roots. So this would equal r1 r2 plus r1 r3 plus r2 r4. And if I called these roots, these letters right here, then maybe what I'm looking for could be C over A. And maybe these are not, by the way, the A, B, and C are not this A, B, and C. I'm just using the generic terms that would go there in my memory space. So this is the formula that I memorize it with. But if we made these those roots, and what if I let A just equal 1? Just see what happens, and you kind of explore this, and you say, okay, then it would just be C would be this expression right now. And so you say, okay, well, this would be the sum of the roots. which would be the negative version of this. Again, if we let a equal 1, the sum of the roots of the cubic is going to be negative b over the leading coefficient, which I'm calling 1, so we don't care to write the 1. And you play around with this for a while, and you kind of, maybe this could work, maybe it won't. And ultimately, I did not find a solution with this path. And so you kind of go, all right, so what do? We kind of go back to the drawing board. And again, I mean, that's really what creative solving is about. You try different things out. You figure out where things work or where they don't. And it's not, you kind of think people don't necessarily take this question and they go, oh, I know exactly what to do. I mean, there's a few people who do. I'm sure there's people much smarter than me who just go, oh, this is going to be simple. I just do such and such, and they just blitz through it, no problem. And those students probably got really far in the contest. But for most of us, you're going to have some false starts. You're going to have things that you try that are ineffective. And I think that's okay. Real problem solving is not about I know what to do and I do it. That's memorization. Instead, what we would like to do is kind of try things until something works, and don't just give up so easily. Now on the contest, it's a 75-minute contest. And so you have an average of 3 minutes per question for the 25 questions. So you can't sit too long with the false ones, but what really happens is you go pretty quick, ideally in 1 to 10. You get those done in 10 minutes or something. So you've saved 20 minutes time off those averages. And then you can invest some of that extra time on later problems in the test so that you have more time there. Okay, so then if none of those things worked, and maybe they do work, by the way, I just didn't find a solve path that way. I felt, I felt adversity. And as I started to feel that pushback from the problem, I thought, this probably isn't what they had in mind. Let's go back and look again at what it says. Sometimes we dive in and we're just like, let's algebraically manipulate and move things around. And there's nothing wrong with what we tried. It could have worked on other problems. It might have generated a solve path. Indeed, it might still generate a solve path. But we might want to go back and see what else there is. So you go back and read more carefully. And it goes, integers. Integers. Well, those have properties. And more properties than I have, actually. And integers, you can do things with them like number theory. So maybe we can get this to a point. Can we just guess and check right now? Like C is 1 and the product of A and B is 99. Seems like it might take a while. But maybe we could get something if we didn't just add them. And it's very tempting to add, right? You get that thing you're looking for, but what if we didn't? What if we instead subtracted the equations and just experiment? You see what you don't do. You don't say, well, except I kind of did over here, but I can tell you I explored it a little while on my paper and didn't find it. You don't typically say, I'm not going to do that, it's not going to help. That's where defeatism is. Instead, you just do it and then you see if it helps. So I'm going to take this, and I just noticed when I thought about subtracting, hey, the difference in these two is 13, and that's a prime. Let's see what happens when we do that. So AB minus BC, just subtracting these two. I'm going to factor out that B, and I'm going to get A minus C when I factor out this subtraction. Then I'm going to have C minus A, otherwise known as the reverse of this, but I would really like them to match. So I'm going to pull that negative sign out. So what I have is C minus A, but I'm going to take the negative out, which will reverse the subtraction. So now we'd have it looking like this, and of course 100 minus 87 is 13. So then you go, this is wonderful. It's exactly what we were looking for. We factor out the A minus C expression, and there's a 1 coefficient here, and when you factor it out, you're left with B minus 1. And the wonderful thing about it is this is going to be an integer, because you have an integer and you subtract an integer, and the set of integers is what we say as closed under subtraction. So all results will be an integer, and this will also be an integer. And so we say, okay, it's a little bit like a Diophantine equation now, where I can kind of say this could be 13 and this 1. Let's see what that would look like. B minus 1 is 13, A minus C is 1, or we might have B minus 1 is 1, and A minus C is 13. It could be either one, right? And this is kind of a natural progression of thought. And we'll go ahead and try this first. The thing we should attack is the one that's definitive. It's definitive when we have B. We have definitively that if this is the case, that B will equal 14, and if this is the case, B is 2, 100%. Now, at this point, where do we test them out? Maybe up here? Maybe I go right here and put the 14 there and here. Let's see what would happen. I would get, if I let B is 14, I would get 14A plus C equals 100, and then I would get 14C plus A equals 87. And this is kind of where you pick up. The problem becomes what we might call in the contest language a time sink. It's an opportunity to save time versus your competitors, or it's an opportunity kind of in the opposite direction, not really an opportunity. You might waste so much time that you miss out on the rest of the questions. And it's all dependent upon what is your perception of the things that you're working with, your tools that we're creating. This is a tool, this factorization, subtracting a tool. A product is a tool, a prime number, a tool. And so we say, how can I most efficiently work through this problem? And in the contest, you're making that decision under pressure. And that pressure is the chance to get to the second round, which approximately 0.0001% of the students in the United States get to. Only a very small percentage of students take the test. They're typically the best students in the country and internationally that want to challenge themselves. And so they take on the challenge, and within that group of people, a small percentage of them, about 6,000 or 7,000, makes it. But there's about 35 million eligible students, and the test is pretty self-selecting. So who's going to make that decision more quickly and process the information? That's the difficulty. So we come over here. I notice if I add these two, I get 15 times the sum of A plus C, which would mean the sum of these would have to be a multiple of 15. But 187 is not a multiple of 15, so this cannot possibly be what it is. But we have found a method to attack it. And so we just go immediately to the next one over here, and you plug in the 2, and it's just swapping out the 14, right? So you have 2A plus, and you have to even write it. Do we have to write it? We shouldn't really have to write it, right? Just picture this as a 2, and that's a 2. And you've got 2A plus A, so 3A, and this is 3C, and you factor out the 3, but 187 is also not a multiple of 3, because 8 plus 7 would be, but the 1 is not. Divisibility rules for 3 is that the sum of the digits would need to be also a multiple of 3. You prove that in AOPS Intro to Number Theory or any number theory course. So what do we do then? Wait a minute, I thought this had to be, everything's here, why doesn't it work? And there's a little bit of moment of, what happened? Did I make a mistake? Did I do something wrong here? Let's go back again. And what did it say? Did it say positive integers? It did not say positive integers. It said integers, but most students, it's just pretty natural. Most people will infer positivity there. Now some don't, but you infer it and you try these positive results, but then you go back and there's a little bit of a moment of, okay, there's still more things I can do. I didn't necessarily make a mistake. This is probably just not the ones that work because we need to look at the negatives. And so we're going to go back and look at b minus 1 equals negative 1 or b minus 1 equals negative 13. We're not even writing the a minus c now because we've already perceived what the game is. The game is focus on the b value. So I could write that a minus c is negative 30, so on and so forth, but let's just not. Let's go and take this negative 1 and put it right back into these original two equations. So you're going to have, if I put negative 1, if I have this equation, b is actually 0, and over here you'd add 1 to get negative 12. So I'm going to try the 0 in here, and I would just get c equals 100 and a equals 87 if I did that. But if c is 100 and a is 87, b being 0, what is 100 times 87 down here? It's bigger than 60 by a long shot, right? So the b cannot be 0, so it must be that b is negative 12. And we have to cross our fingers and hope. If our reasoning was sound, then at this point we finally settled upon the correct value that works. And now it should just be, for the students taking the contest, a race to the finish line. However, we might have also made a mistake, and you have that little bit of trepidation that if that doesn't work, then what? Now we've wasted all this time in our time sink and didn't get any fruit to bear for it. So let's come back over here and drop this negative 12 in. And again, from the student's perspective, you have that, oh, please work, please, I need you to work right here. So you drop it in, you're going to get negative 12a plus c equals 100, and negative 12c plus a is 87. So when we add these two, we get negative 11a plus c equals 187. And so we go, well, that's definitely a multiple of 11. For those of you who might not know watching this video, anytime the sum of the outer digits adds to the middle digit, that's the product 11 times those outer digits, 17. That's the 11's trick for two-digit multiplication. 11 times 34, for instance, is 374. You just add the two and drop it in the middle. Just covering this concept for those people watching who might not know. In addition, if you do 11 times something that would go over 10, like 5 plus 8 is 13, you'll keep the 8, you'll put the 3 units digit and carry the 1. It would equal 638. These tricks are very important for students taking the contest to save time and not waste so much time on the time sink. And so you come over here, then a plus c would have to equal this negative 17, because this is obviously a positive number, and a negative times a negative will make it positive. So now you have a plus b is negative 17. And so you say, okay, what else can I do? I can also come down here, CA, because you're not quite out of the woods yet, CA plus B is 60. Now B again, being negative 12, when I add it to the other side, gives 72. And so now we just have to think, if A and C are also both negative, then they would multiply to a positive. And most students, what are we doing right here? It's basically factorization, right? What would it be? It would be the factorization of x squared, and these would be like your roots, right? So you would want a sum of your roots of negative 17, so you'd have plus 17x, and then you'd have plus 72 equals 0. It's the roots of this quadratic. And anytime you got to this point when you were in Algebra 2, you would quickly go, oh, what two numbers multiply to this and add to this? And if you were good at it, you know it's 9 and 8. And that's the same concept that we're doing here, but we're not really in a quadratic factorization situation. We're just perceiving, hey, negative 9 and negative 8 would add and multiply, and that's it. You now have, it doesn't matter what's what, to be honest. I mean, I guess you could figure it out if you let negative 9 be A, and you let B be negative 12, and then C being the negative 8. 108 minus 8, it is 100. It works, right? And why would you check this in the contest? Why bother to check? Because as smart as students are, they're very clever, the test makers, and they might very easily make something that looks great on the surface, but doesn't actually work out. And a lot of students get 0 points at that point, because they didn't bother to check themselves. So this is basically a safety net called I have humility, and I'm gonna check because I've seen myself make so many mistakes in the past. That one works, and if you're still not certain, check another one. Again, if B is negative 12 and C is negative 8, this is 96 minus 9, it's 87. Check the last one just for good measure. C is negative 8 and A is negative 9. That's the 72. We already checked it. We know it works. Minus 12 is 60. So at this point, you're just going to come over here and do this. And you could get cute and factor out a B if you wanted. But honestly, just find each of the pairwise products and go. And you already know that CA is 72. We already found that. And we found this one and we saw that it was 108. So we're at 180 right now. And we found this one and it was 8 times 12, but the positive version 96. And so you have 180 and 90, 270 plus 6 more, 276. That is 180 plus 90 plus 6, 276. Answer choice D. So again, I closed it out kind of as quick as I would on the test because that's the way you take the test, is at speed. And so that's it. I hope you enjoyed the solution that I found. And as always, I will see you in the next newsletter, number 25. It comes out in September. Again, check out IGMCG. They're a great group to be a part of.